Hello and good day everyone. Today we are going to look at Chapter 6, Ordinary Differential Equations, or ODEs. Let's say that we have a function of y equals to f of x, where x is independent variable and y is dependent variable. As we differentiate the function with respect to the independent variable, 1 time, 2 times and so on, we obtain its ordinary derivatives as dy over dx, d square y over dx square and so on. An equation that consists of the function y equals f of x and its ordinary derivatives is called ordinary differential equations. A few examples are as follows. The solution of an ordinary differential equation is a function y equals f of x satisfying the ordinary differential equation. Now we will look into initial value problem. An initial value problem is an ordinary differential equation together with a specified value, called the initial condition, of the unknown function at a given point in the domain of the solution. Consider an IVP of the first-order differential equation as follows. The IVP can be solved by using two numerical methods. One of them is Euler's method, and the other is fourth-order Runge-Kutta method. However, we will only look into Euler's method for this chapter. Given the general first-order ordinary differential equation with the following initial value boundary condition. By using numerical method, the interval of x is divided into n subintervals with width h, such that xi equals x naught plus ih. We need to solve for y from I equals 1 to n. Notice that by using numerical methods, we only obtain discrete values of y. But by solving the differential equation analytically, we obtain a continuous function of y of x. The solution by Euler's method is given by the following formula, where h is the step size. Let us dive into our first example of using Euler's method. Solve the initial value problem of y prime equals x squared times 1 minus 3y, given that y0 is 1 and x equals from 0 to 0.5 with a step size of 0.1 by using Euler's method. If the exact solution is y equals 2/3 by the exponential of minus x cubic plus with 1/3, find the absolute errors. To solve this problem, firstly we need to tabulate the x values, then we reserve a column for the new y values that we will calculate using Euler's method, the exact values of y, and finally the absolute errors. For the exact values of y, it can be found from the given exact solution from the question, so we can easily fill it up first. The value of y0 is given as well. To calculate the subsequent new y values, we'll be using the formula for Euler's method with h interval equals 0.1 and function of f taken from the question which equals to x squared by 1 minus 3y. By simply following this formula, we will get the value of y1 for initial 0th iteration, y2 for the first iteration, y3 for second iteration, and so on. All of the absolute errors can then be calculated. Let us move to example 8.2. Suppose that 25 tigers are released into a game preserve. Initially, the population grows at a rate of approximately 30% per year, but because of limited food supplies, the preserve is believed to support only 40 tigers. The population model of tigers is given by the following equation. Find the population of tigers for the said time interval by using Euler's method with h equals 1. So based on the Euler's formula, we can key in the required information as follows, with the initial 0th iteration, P0 being 25. Similar to the previous example, we can now easily solve the problem by using the obtained formula up until 10th iterations following the required time interval. That's all for our session today. Stay tuned for the next part.